Alright, let's start our journey into oceanography by establishing the fundamental framework of Earth's surface. We are looking at the hypsographic curve. Now, ध्यान से सुनो, ये कोई complex mathematical graph नहीं है. It is simply a cumulative frequency curve that helps us visualize the relationship between the area of Earth's surface and its elevation or depth. Why do we need this? Because maps can be deceiving. A map shows you location, but this curve shows you the distribution of area at different vertical levels. The reference point here is the datum line, which we consider as the mean sea level or MSL. Everything above is land, elevation, and everything below is ocean, depth. Look at the shape of the curve in the slide. Notice distinct steps. You have a small percentage of very high mountains, then a broad plateau of continental land, and then, pay attention here, a sharp drop. This drop represents the continental slope leading us into the deep ocean basins. The curve flattens out again at the bottom. This tells us a fundamental geological truth. Earth has two distinct crustal levels. एक है lighter continental crust with average height around 840 meters और दूसरा है dense heavy oceanic crust with average depth around 3800 meters. This bimodality, though अलग-अलग levels का होना, confirms that continents and oceans are structurally different, not just random ups and downs. The curve clearly demonstrates the dominance of water. Oceans continental landmasses के comparison में बहुत ज़्यादा vast और deep हैं. Now, shift your focus to the global balance shown in the pie charts. There's a massive asymmetry here. The northern hemisphere is often called the land hemisphere because roughly 40% is land. यहाँ civilizations, agriculture, and major river systems dominate. Contrast this with the southern hemisphere, the water hemisphere, where water covers a staggering 81%. This isn't just a trivia fact. It implies huge climatic differences. सोचो जरा, water heats and cools slowly, right? So the southern hemisphere has a more moderate oceanic climate compared to the extreme continental climate of the north. This distribution dictates everything from wind patterns to ocean circulation. Simple है. The geography of land and water is the stage on which the climate system performs. Clear है?
Moving deeper, let's leave the shoreline and walk into the ocean. We are entering the continental margins. ये वो transition zone है जहाँ continent खत्म होता है और actual deep ocean floor शुरू होता है. It has three distinct parts: the shelf, the slope, and the rise. First is the continental shelf. Technically, this is still part of the continent. It's just flooded. Geologically, it is continental crust. Look at the gradient. It's very gentle, almost flat, 1 degree or less. Why does this matter? Because shallow water means sunlight can reach the bottom. Sunlight means photosynthesis, which means plankton, and ultimately massive fish populations. That is why the world's richest fishing grounds, like the Grand Banks or Dogger Bank, are always found on wide continental shelves. Economically, this is the most valuable real estate in the ocean. Oil, gas, and placer deposits सब यहीं मिलते हैं. But notice, shelves aren't uniform. The Siberian shelf is massive, 1500 kilometers wide, because the Arctic coast is passive and tectonically stable. In contrast, the Chilean coast has a very narrow shelf because the Andes mountains are rising right there due to plate subduction. वहाँ shelf compress हो गया है. Now, walk further out to the shelf break, suddenly the flow drops. This is the continental slope. The gradient increases sharply to 2 to 5 degrees. This is the true edge of the continental block. Here, you often find deep cuts called submarine canyons. How do these canyons form underwater? Rivers can't cut them there. The answer lies in turbidity currents. Think of them as underwater avalanches. Sediment-laden heavy water rushes down the slope at high speed, carving out these V-shaped valleys, like the Hudson Canyon. It is a strictly erosional feature. Finally, where this avalanche hits the bottom, it slows down and dumps its load. This pile of sediment forms the continental rise. It connects the steep slope to the flat deep sea. So the sequence is logical: shelf, submerged land, slope, the drop, rise, the debris pile. Understanding this profile is crucial because it governs where resources are found and how sediments are transported from land to the deep abyss. Clear logical chain बन रही है ना? Good.
अब हम कॉन्टिनेंटल राइज को क्रॉस करके डीप ओशन में एंटर कर रहे हैं। Welcome to the Abyssal Plains. These are the flattest surfaces on planet Earth, even flatter than the flattest plains on land. But why? Is the ocean floor naturally smooth? No, absolutely not. The original volcanic crust underneath is rough and jagged, just like the Himalayas. But over millions of years, sediments falling from the surface have blanketed this roughness. It's like snowfall covering a rocky field. Eventually, the surface looks perfectly smooth. That is how abyssal plains are formed, by the extensive blanketing of Terrigenous, that is land-derived, and shallow water sediments over irregular topography. Let's decode the composition of this sediment. It's not just mud, it's history. We have Biogenous oozes, which are essentially the skeletal remains of microscopic marine organisms. There are two main types based on chemistry: calcareous or calcium carbonate and siliceous or silica. Here lies a very important concept called the CCD, carbonate compensation depth. Listen carefully. Calcium carbonate dissolves in cold, high-pressure water, which is acidic. Deep ocean water is corrosive to calcium. So if these shells fall below a certain depth, the CCD, usually around 4 to 5 kilometers, they dissolve before forming sediment. Therefore, you find calcareous oozes like Globigerina on shallower ridges or elevated plains, not in the deepest trenches. In the deepest, coldest parts where calcium dissolves, you find siliceous oozes like diatoms or radiolarians, because silica doesn't dissolve as easily there. Or you find red clay. Red clay is pelagid deposit, very fine dust from volcanoes, windblown sand from deserts, and even meteorite dust from space. Since it accumulates incredibly slowly, it dominates areas where no other sediment reaches, like the vast Central Pacific. Speaking of geography, look at the distribution map. The Atlantic Ocean has huge abyssal plains because giant rivers, Amazon, Congo, Mississippi, dump tons of sediment there. The Pacific, however, has fewer plains. Why? Because the Pacific is surrounded by trenches. Trenches act as traps. Sediments from land fall into the trenches and never reach the central ocean floor. Samajh aaya logic. Atlantic fills up, Pacific traps it at the edges.
Now, let's swim to the center of the ocean basins to witness the most dynamic geological feature on Earth, the Mid-Oceanic Ridges, MORs. This is not just a mountain range, it is a factory. It is the longest continuous mountain chain on the planet, stretching over 70,000 kilometers, wrapping around the globe like the seam of a baseball. But unlike mountains on land formed by collision, MORs are formed by separation. This is a divergent plate boundary. Tectonic plates are pulling apart here. As they separate, the pressure on the mantle below decreases, causing the rock to melt, decompression melting. This magma rises up to fill the gap, cooling to form new oceanic crust. That is why we call it a constructive margin. Nai zameen ban rahi hai yahan. Structurally, it's distinct. It's not a sharp peak, but a broad ridge with a central rift valley running down its spine. This valley is the scar of the pull-apart force. You will also see fracture zones cutting across the ridge perpendicularly. These are scars where the ridge has been offset by transform faults, accommodating the curvature of the Earth. But the most fascinating part is the hydrothermal systems. Seawater seeps down into cracks in the newly formed hot crust. It gets superheated by the magma, dissolves minerals, iron, copper, sulfides, and shoots back up into the freezing ocean. When this hot mineral-rich fluid hits cold water, the minerals precipitate instantly, looking like black smoke, hence black smokers. Imagine life here. No sunlight, crushing pressure, toxic chemicals, yet life thrives. Tube worms and giant clams live here not by photosynthesis, but by chemosynthesis. Bacteria convert the toxic sulfides into energy. This discovery revolutionized biology because it proved that life doesn't strictly need the sun, it just needs energy, even from the Earth's belly. Basic concept को visualize करो. Cold water goes down, gets heated, picks up minerals, shoots up, and sustains an alien ecosystem.
Let's move away from the ridge and look at individual volcanic features. Seamounts, Guyots, and atolls. Not all volcanoes are part of the ridge system. Some are solitary warriors formed by hotspots, plumes of magma punching through the moving plate, like the Hawaiian chain. A seamount is simply an underwater volcano that rises more than 1,000 meters but doesn't reach the surface. It stays submerged. But what happens if it does reach the surface? It becomes a volcanic island. This brings us to the story of the Guyot, pronounced Geo. Look at the diagram. A Guyot is a flat-topped seamount. But nature doesn't build flat-topped volcanoes. It builds cones. So how did it get flat? Logical reasoning, Legao. It must have been an island once. Waves eroded the top, planing it off flat at sea level. Then the crust beneath it cooled and became dense, causing the island to sink, subsidence, or the sea level rose. So a Guyot is essentially a drowned, eroded island. This subsidence is crucial evidence for plate tectonics. It proves that the seafloor moves away from the heat source and sinks as it cools. Now, integrate biology with this geology, coral reefs. Darwin gave us the subsidence theory to explain atolls. Imagine a volcanic island. Corals start growing along the shore. This is a fringing reef. As the island slowly subsides, sinks due to plate cooling, the corals grow upwards to stay in the sunlight, or photic zone. A lagoon forms between the sinking island and the reef. Now it's a barrier reef. Finally, the island completely sinks below water, leaving only a ring of coral on the surface. That ring is the atoll. So an atoll is basically a grave marker for a sunken volcano. The diagram shows this evolution clearly. Stage A, fringing, to Stage B, barrier, to Stage C, atoll. Without the sinking of the crust, you wouldn't get this sequence. Everything is linked. The plate moves, the volcano sinks, the coral grows up. Simple, right? From the mountains, we go to the deepest voids, the ocean trenches. These are the deepest parts of the ocean, often exceeding 10,000 meters. The Mariana Trench, for instance, is deeper than Mount Everest is tall. Morphology-wise, they are narrow, steep-sided, arcuate, bow-shaped depressions. But why are they here? Trenches represent convergent plate boundaries. This is where the old, cold, and dense oceanic lithosphere collides with another plate and dives or subducts into the mantle. It is a zone of destruction. Look at the cross-section. The heavy oceanic plate is sliding beneath the lighter plate. This friction creates massive earthquakes. The zone of earthquake foci inclined into the mantle is called the Benioff zone. As the plate goes deeper, it melts, sending magma up to form volcanic arcs like Japan or Philippines, parallel to the trench. Note the distribution. Trenches are not randomly scattered. They are concentrated in the Pacific Ocean, forming the Ring of Fire. Why the Pacific? Because the Pacific plate is actively subducting along almost all its margins. In contrast, the Atlantic and Indian Oceans have fewer trenches. Why? Because their margins are mostly passive margins, where the continent and ocean floor move together without colliding. However, there are exceptions like the Puerto Rico Trench in the Atlantic or the Sunda Trench in the Indian Ocean. But generally, the Pacific is shrinking due to these trenches consuming the floor, while the Atlantic is expanding. The depth of the trench often depends on the age of the subducting plate. Older plates are colder and denser, so they sink at a steeper angle, creating deeper trenches like Mariana. Younger, warmer plates resist sinking, creating shallower trenches. Concept clear, hey? Trenches are the graveyards of the oceanic crust. Now that we understand the features, let's do a regional comparative analysis of the three major oceans, Atlantic, Pacific, and Indian. Each has a unique personality based on its tectonic history. Start with the Atlantic Ocean. Look at the map. It has a distinct S shape. This is an ocean that is opening up. Its defining feature is the Mid-Atlantic Ridge, or MAR, which runs exactly through the center, splitting into the Dolphin Rise in the north and Challenger Rise in the south. Because it has passive margins, the continental shelves are very extensive. Look at the Grand Banks or Dogger Bank. These are broad, shallow platforms perfect for fisheries. The Atlantic connects the Arctic to the Antarctic, making it the only ocean to stretch fully north-south. Contrast this with the Pacific Ocean. It is circular, vast, and covers 1/3 of the Earth. It is a closing ocean. Its ridge, the East Pacific Rise, is not central, it's shifted to the east, and unlike the Atlantic's slow-spreading ridge, this one is fast-spreading, so it's broader and less steep. The Pacific is dominated by trenches, ring of fire, and thousands of islands and seamounts, over 20,000. The complexity here comes from the interaction of multiple small plates and hotspots. Finally, the Indian Ocean. It has a unique Y shape or inverted Y shape configuration. The central Indian Ridge comes down from the north and bifurcates or splits near the Rodriguez Triple Junction into the southwest Indian Ridge and southeast Indian Ridge. A very special feature here is the submerged ridges, like the Lakshadweep Chagos Ridge. This is a linear trace of a hotspot, the Reunion hotspot, that India passed over as it moved north. Also, look at the basins. The Bay of Bengal contains the thickest sediments in the world, the Bengal Fan. Why? Because the Ganga and Brahmaputra rivers are eroding the Himalayas and dumping all that mud here. The Indian Ocean is also unique because it is landlocked to the north by the Asian continent, which drives the monsoon system. Though that's a climate topic, the basin shape causes it. Physically, it is a complex mix of ridges, plateaus like Kerguelen, and massive sediment fans. We conclude with the floor itself, marine sediments, and the resources they hold. The ocean floor is the ultimate repository of Earth's history. We classify sediments based on their source. First, Terrigenous, derived from terra, land. This is gravel, sand, and silt brought by rivers and wind. Naturally, these are dominant on the continental shelves and slopes. Second, Biogenous, derived from life. As we discussed, these are the skeletons of plankton, calcareous or siliceous. Third, Hydrogenous, formed from water chemistry. These precipitate directly from seawater, like salt evaporites, or the metallic nodules we will discuss shortly. Fourth, Cosmogenous, distinct dust from meteorites. It's rare, but present. Now, focus on the economic implications. Polymetallic nodules, PMN, also known as manganese nodules. These are potato-shaped lumps found on the deep abyssal plains. How do they form? It's a chemical process. Metals like manganese, iron, nickel, cobalt, and copper, dissolved in seawater, start precipitating around a nucleus, maybe a shark's tooth or a piece of shell. Layer by layer, like a pearl, they grow. But the growth rate is incredibly slow, millimeters per million years. Yet, there are trillions of tons of them lying on the ocean floor. Why are they important? Look at the composition. Nickel, cobalt, copper, these are the critical metals for the battery revolution, electric vehicles, EVs, and renewable energy storage. As land reserves deplete, the deep ocean becomes the next mining frontier. Geography dictates geopolitics here. The Central Indian Ocean Basin, CIOB, is rich in these nodules. India has secured the status of a pioneer investor and has exclusive mining rights allocated by the International Seabed Authority, ISA. This is huge. It means India has strategic access to resources essential for a high-tech future. But the challenge is technology and environment. How to vacuum these potatoes from 6,000 meters deep without destroying the fragile abyssal ecosystem. That is the question for the future. So, sediments are not just dirt. They are the archive of the past and the resource bank for the future. Submerged? This connects physical geography directly to economic geography. Good. This concludes our rigorous breakdown of oceanography basics.